Okay, so in the last video we talked about K, what K means, what the term favor means versus what shift means, and a little bit about Q. Let's kind of continue breaking it down. Q, again, is called, or is a reaction quotient, is its name. It is the same expression and the same calculations used to calculate K. So if Q and K are mathematically the same thing, it is important to recognize that they are different in how we use them and what they mean. K is for at equilibrium, meaning this is the ratio of products to reactants when we have reached equilibrium. Q is our test, okay, a way for us to look at whether a set of scenarios is at equilibrium or not. And then from there, it allows us to know which direction the reaction will shift, not favor, but shift to reach equilibrium. Okay? And then, of course, any concentration that is zero, so let's say if I had 0 nitrogen or 0 hydrogen, we would know that there never can be 0 and equilibrium. It would have to shift in that direction. And if I had 0 ammonia, it would have to shift in that direction. So 0 automatically tells us what direction something is shifting, which is going to become very important as we progress through this. But we can use Q when there's not a 0 to determine which direction we are going to be shifting. Okay, so let's kind of talk about that. First and foremost, when Q is equal to K, that means the ratio of products to reactants is already at equilibrium. So no shift will occur. Equilibrium has been reached. We're done. Okay? If Q is greater than K, what that essentially means, again, if we think back to our ratio of products to reactants, it means our products are too large or our reactants are too small. So what's going to happen is we're going to have a shift towards reactants. We need our denominator bigger, we need our numerator smaller. That means we're going to have a shift towards the left. So if we think reactants to products, we're going to have a shift towards reactants. Regardless of what the size of K is, if Q is larger than K, it's going to have to form reactants to get to K. It means the ratio is off. Okay, if Q is smaller than K, okay, again, thinking products over reactants, it means our reactants are too large, our products are too small, so reactants are going to be shifting to form products. So again, if we think reactants forming products, we're going to see a shift towards the right side of the reaction. Now, one of the shortcuts I've kind of seen with this is when you're comparing the value of Q and K, put K first. Alphabetical order, if you will. So if K is less than Q, notice which direction the alligator mouth, if you will, is pointing. If we were to make that an arrow, it's pointing to the left. Well, if Q is greater than K or K is less than Q, we get a shift in the left-hand direction. If K is greater than Q, we get a shift in the right-hand direction. Now, this is nothing more than a mental check. This is not an explanation. You still need to be explaining why that shift is occurring, which comes down to the fact of products to reactants, that ratio, and what needs to happen to get that ratio to equilibrium. So again, Q tells us shifting, K tells us favoring. So two very distinctly different things. Once K has been reached, we can then look at the amount of reactants and the amount of products and say who is being favored. And again, the more reactants are being favored. The more products are being favored. So let's just kind of look at this in terms of a couple problems. So we have a bunch of scenarios here, okay? We have a reaction, which is Haber process of nitrogen plus hydrogen forming ammonia. And we could have Q or K, either one can be our variable here. And we're told that K at 500 degrees Celsius is equal to 6.0 times 10 to the negative second. So let's pause. K tells us favoring. So which species are favored in this particular reaction at this particular temperature. Take a second, pause, think about it. Okay, because K is less than 1, and we're looking at a ratio of products to reactants, it means there are more reactants than there are products. Our denominator is bigger than our numerator. What that means is our reactants are favored in this equilibrium. Okay, that has nothing to do with shifting, which is what this problem is actually going to be asking for, which is what has to happen to reach equilibrium. This is just a practicing using K and seeing what K stands for. So, with that being said, let's talk about these scenarios. We're given a series of scenarios, our concentrations, and we're asked to determine, are we at equilibrium or are we not? How do we do that? We compare Q versus K, given that K is 6.0 times 10 to the negative second. So all we're going to do is plug in these values into our equilibrium expression. So our first Q, QA if you will, is going to be equal to 1.0 times 10 to the negative third to the second over 1.0 times 10 to the negative fifth to the 1 and 2.0 times 10 to the negative third to the third. So take a second, solve this out, and see what you get. Okay, so when I do this, I'm getting a Q value that's equal to 1.25, or technically with proper sig figs should be 1.3, because everything's 2 sig figs here, times 10 to the 7th, positive 7th is what that looks like. So how does Q compare to K? Well, Q is massive compared to K. Again, that doesn't really mean anything in terms of shifting speed or anything like that, but it does mean there's going to be a very large shift towards which side of the reaction. What do you think? Okay, well, if Q is greater than K, again, if I'm looking at products over reactants, it means my products are way too big, or my reactants are way too small, however you want to think about that mathematically. So we're going to see a shift towards reactants, or a shift towards the left side of this equilibrium, okay, to reach equilibrium. All right, let's keep going. Let's do the next scenario, and we'll go through and do these 3 scenarios, and then we'll look at K and how to solve for K. Okay, so here, I'm going to have my Q in this case being 2.0 times 10 to the negative fourth to the second over 1.5 times 10 to the negative fifth. I'm not sure why there's an extra parentheses there, sorry about that. And then 3.54 times 10 to the negative 1 to the third. This guy down here is going to be Q is going to equal 1.0 times 10 to the negative fourth to the second over 5.0 to the 1, and then times 1.0 times 10 to the negative second to the third. So do me a favor, take a second, solve these 2 values, and I want you to try to predict which direction the reaction will shift to get to equilibrium. Okay, so if I go through and do these calculations, I'm getting this Q to be around, again, 2 sig figs, because this guy's 2, technically both of these are 3, to be 6.0 times 10 to the negative second. And this guy down here, if I was to go through and do my calculations, I am getting Q equals 2.0 times 10 to the negative third. So let's just go back up and look at what K value is again. K is 6.0 times 10 to the negative second. Okay, we'll check out what we just got here in the second scenario. Q is actually equal to K. So what does that tell us? That tells us that this is an equilibrium position, meaning these concentrations, these ratios of concentrations, will give us a value that is equal to K, meaning we are at equilibrium in this scenario, so there will be no shift that will occur for this scenario, scenario B. Down here, though, if we were to look at it, Q is actually less than K. Q is smaller than K. So what does that mean? That means products over reactants. If I was to look at that, that means my products are smaller than they should be, or my reactants are bigger than they should be, however you want to think about that, which means I'm going to get a shift towards products or a shift towards the right side of the reaction. Okay? Okay, so I'm going to stop here in this video. So now we've had a chance to look at what Q is, what K is, and then how we can use K to determine favoring and using Q to determine shift if there is going to be a shift. In the next video, we're going to look at K and how to use K to solve equilibrium problems. So thanks, guys. Keep up, and we'll keep going from here.